Back in the golden age of radio of the 1940s, the iconic tagline for The Adventures of Superman lauded the superhero as being faster than a speeding bullet, more powerful than a locomotive, able to leap tall buildings at a single bound. If a new electronics packaging technology could make things run faster, handle more power, and, well, maybe not leap tall buildings, but keep cool in these situations, we could definitely say that this new technology is super. Today's Tech Chat is sponsored by Mouser Electronics, and we are looking forward to talking about advances in silicon carbide power modules from Wolfspeed. If you aren't familiar with the company name Wolfspeed, it is because until October of 2021 they were known as Cree. But whatever the name, this is a company that has been leading the development of advanced silicon carbide materials and products for decades. Joining us on Tech Chat is Jonathan Hayes, an applications engineer in power modules at Wolfspeed. Welcome, Jonathan.
Thank you, Dale. I'm glad to be here to discuss our exciting new technology.
So as we get started here, why don't you give us a quick intro on what you will be educating us about today?
Sure. So we've recently released a new power module platform within the last year called our Wolfspeed Wolfpack family. And what this is a base plateless power module platform. And so actually recently we've released the second iteration of this platform, the GM3 module. So really what I'd like to talk about today is how you can scale your present system based on our smaller FM3 style Wolfpack package, how you can scale it up with the GM3 and kind of talk through some of the performance enhances that would be possible with this new GM3 platform.
That sounds great. When I started in the electronics industry, let's just say some time ago, nobody was really talking about or using silicon carbide very much. So tell us why silicon carbide is seeing rapid growth recently and how Wolfspeed is involved in this growth.
Sure. So I have two questions. The second question of why silicon carbide has been the focus of quite a bit of research, over the last decade or two, mainly due to all the performance benefits that the material silicon carbide can provide as a power semiconductor device, especially at the higher voltage levels, say 1200 volts and above. So really what silicon carbide enables, as we talk about it as a MOSFET power device, is faster switching speeds, which of course correlate to lower switching losses. So everybody would like a higher efficient system. And as we go to a more electrified world in automotive and energy storage and renewables, high efficiency is a very important topic and performance desire that most engineers are going for. So the benefits of silicon carbide are quite well known, but the second question is why Wolfspeed? And I think we have an extensive track record in silicon carbide production as a vertical supply chain, all the way from the base material through bare die, discretes, and even power modules. So we have the expertise in-house to fulfill all of your silicon carbide needs. And throughout the years and over the years with our 10 plus years of MOSFET experience and 17 years of diode production, we've seen widespread adoption, and we have over 7 trillion field hours of devices out in the field operating and providing the performance benefits that we recently discussed. So, and not only do we have this track record, but we're also investing for our future. So we understand where the market is heading and the need, especially for silicon carbide. So we're looking to invest to reach, over 30 times capacity in the near future.
That's great. And that focuses on the advanced capabilities of Wolfspeed's silicon carbide semiconductor technology. But today you're going to be talking to us about another important aspect of Wolfspeed's products, advanced packaging.
That's correct. Again, our latest platform, the Wolfspeed Wolfpack family, is a base plateless module design. So within this family, there's different levels of module size, and we're actually introducing a second variant called the GM3. And this GM3 package is slightly larger than the smaller FM3 that we've previously released over this last year. But really the features remain the same, and how it's utilized and eventually used by the end user is all the same. It's just a larger housing. So essentially we can accommodate more die and actually push the RDS on lower than the FM3. So it kind of fits a new power range.
So I'm going to freely admit my ignorance here. This package looks absolutely nothing like just about everything that goes into consumer electronics and the products I've worked on in my career. Now, maybe you're going to talk about this later, but how are these types of packages assembled into PCBs, and how are the connections made to those press fit pins?
Yeah, so I've mentioned it's a base plateless design a few times now, and what this means is that it's actually very easy to use. So we don't have a base plate. The interface is a DBC substrate on the bottom, so that can mount directly to a heat sink or a cold plate with the use of thermal interface material or thermal paste. And we really get the performance thermal benefits from that from not having a base plate. But also, not having a base plate means that this is a more cost-effective module. So, really getting rid of that cost, we become more competitive from a cost perspective at these kind of lower power levels, where we actually are starting to creep into maybe some of the applications that utilize discrete components. But with that, one of the themes of the Wolfpack family is to be very easy to use and implement. So again, we have the base plateless design, but the press fit pins on the other side are designed, again, to be very simple to use from a manufacturing perspective. It's very easy and simple to press in these modules into a PCB. So these are PCB mount modules as opposed to power tabs that need to be bolted to a DC bus structure or something of that nature. But these press fit pins are designed for a high reliability connection. So we get rid of the need to solder, which of course discrete components need to be soldered. But when you get rid of that solder connection, we really increase the reliability of that contact. So again, these are designed to be very easy to use, have simple implementation, and also be cost effective.
Thanks. That really helps. When you talk about high current designs and solder connections, that is understandably a reliability concern.
So again, I just wanted to give an overview of our Wolfspeed Wolfpack family offering. We're adding this new GM3 package. They're all half bridge modules in two on resistance variants, a 6 milliohm and an 8 milliohm. And each one of those on resistance variants has what we call a standard alumina substrate and an optional thermally enhanced aluminum nitride substrate. So the aluminum nitride substrate actually will help you get quite a bit more performance out of the module, but at a relatively low cost increase. So that's a nice option to have in terms of increasing power or loss overhead or decreasing junction temperature for power cycling lifetime capabilities. Again, with this kind of bigger housing of the GM3, we can push the RDS on lower. So our FM3 half bridge modules come in at 16 and 11 milliohms. So you can see we've reduced that by half, roughly half for each variant of the GM3. So these really fit the same applications for both the GM3 and the FM3. The target applications really remain the same. We see adoption in the offboard fast charging market as both active front end and DC-DC converter building blocks, or really any grid-tied converter application where simple design, implementation, and scalability is needed. And of course, these modules are really intended for high power density and high efficiency applications, which most engineers would desire for their intended application.
Now, you mentioned using this new package for the half-bridge versions now. Are you going to be using this package downstream for some of your other products like the six-pack shown here?
That is one of the nice things about this base plateless housing is that it's designed to be flexible and configurable. So as we really targeted our present release based on what's available in the market at this moment, so we can be a direct drop-in replacement or second source for what's out there. In the future, there is the capability and the possibility of extending these offerings to other topologies, such as a six-pack or a full bridge, for instance. So yes, that's always in the works, and we always consider those topologies moving forward as the market dictates.
Oh, that makes sense. And then one of the key benefits you mentioned was simpler cooling systems. A lot of people that may not be living in these worlds may think that is a relatively small benefit, but the long-term cost of ownership can really go down for these things when you reduce the complexity and the costs of the cooling systems in these applications.
That's correct. And most people consider silicon carbide to be more expensive than some of their silicon counterparts. But really, the gain that you get from the system level or the operational costs really outweigh, the nominal cost of the devices, which are coming down. But really, with the ability to implement a simpler cooling system. So you're saving costs at the system level with a smaller heatsink or a higher heatsink temperature because these devices can operate more efficiently at elevated temperatures or across the lifetime of the operation of your application. So any savings that you get in terms of any loss that comes from your converter that you now don't have to reject through your HVAC system or some other means, you're really saving costs on that perspective. And that's something that should be considered when looking at implementing these modules.
Yeah, that's exactly right. So where do these new GM3 power modules fit within the larger framework of the Wolfspeed product offerings?
Like we touched on earlier on not only why silicon carbide, but why Wolfspeed. One of the things as a completely vertically integrated company is we offer products that fit the entire power continuum. So from 1 kilowatt with discretes all the way to 600 kilowatts and above with some of our really high power module solutions. And each is segmented based on what your overall design goal would be. Discrete design goals are different than module design goals. But really the Wolfpack family as a whole kind of bridges the gap between discrete solutions and our high power module solutions. And prior to the GM3, there was really an actual gap between where the FM3 kind of tailed off and where we started to see some of our higher power module solutions take over in terms of the BM or the 62 millimeter power module and the XM3 and those higher power levels. So the GM3 slots really quite nicely into this kind of power continuum from roughly 70 kilowatts all the way up to 170 or even 200 kilowatts. And so again, this adds nicely to our not only our Wolfspeed Wolfpack portfolio, but really our entire product portfolio, which grows with your system power.
It's excellent to see that. And all of these, from discretes to high power modules with FM3 and GM3 in the middle, it's the same silicon carbide technology on the inside, just different packaging. Is that correct?
That's exactly correct. So we are vertically integrated. So we create the material and the wafers and do our own devices and then package our own devices in from discretes to modules. So it's all the same technology. We have different generations of technology, Gen 2 devices, Gen 3 devices, which the Wolfpack is all based on our Generation 3 devices, hence the FM3 and the GM3 naming convention. But yes, it's all the same technology. So really there's no performance letdown or corners cut, I guess, if you will, from a discrete or a module. Really, we have the ability to optimize the die and the number and the layout to fit our packages and push the performance of those packages because we have that controllability.
Oh, it's very interesting.
So really the main focus of releasing the GM3 package is the scalability that you can achieve in your system with this new package, but really with overall with the Wolfspeed Wolfpack product family as a whole. So here we can see that a one-to-one visual comparison of the FM3 of the GM3 and our silicon carbide optimized higher power footprint known as the XM3. So when we talk about scalability and bridging the gap in that power continuum, this is really what we're talking about. So again, the FM3, we have 16 and 11 milliohm half bridge variants, 32 and 21 milliohm six-pack variants. But with that GM3 package, which you can see from this one-to-one comparison, is only slightly larger than the FM3, but we can push essentially half the on resistance and push it down to 8 milliohm and 6 milliohm offerings. So going further to our baseplate module, our XM3, this is where we really get the ultra low on resistance, where we can push it down to even 2.6 milliohms with one of the XM3 variants. So again, this just gives you an idea of how the GM3 bridges that gap between the FM3 and our higher power module solutions, not only in terms of on resistance and power, but in physical size.
I think you kind of alluded to this before, but in the GM3, you're basically putting more silicon carbide inside the package, in parallel basically, to bring the resistance down. Is that what's going on inside?
Yes, exactly. So with the larger physical housing, we have a larger substrate area to work with. So we can essentially fit more silicon carbide active area inside, which translates to more die. And then with the XM3, it starts becoming maybe not necessarily more die, but larger die. So each variant, the FM3, GM3, and XM3, all kind of house a range of die of particular RDS(on) values depending on the size, and then the housing from the FM3 to GM3 is physically larger, so we can house more die compared to the FM3. So that's how we achieve a lower on resistance.
The matching of the FM3 and these GM3 footprints would certainly make things easier for system designers. So I assume that was a big part of your planning.
That's correct. So the main theme that I'd really like to hound home is the scalability and the flexibility of this Wolfpack platform. So the implementation, like we discussed earlier on a heatsink and being a base plateless design, is very similar for each. And even with this, as you can see, the mounting hole pitch actually remains the same from the FM3 to the GM3. So say you had a three-phase converter, an inverter or grid-tied converter of some sort, where you have 3 half-bridge modules. You can see that going from 3 FM3 modules to create your system, if you were to scale that up with the GM3, you're not really using significantly more area. So to scale up in terms of power or switching frequency or power cycling capabilities, for instance, we're really not significantly increasing the physical area. And even with the same mounting hole pitch dimension, the same heatsink can be used for the FM3 and the GM3. So if you know for your end application that you're going to have a wide variety or a wide range of power levels that you need to meet with a certain topology, this is a simple consideration that could be made to, once again, take some of that cost consideration at the system level and reduce the cost from your heatsink perspective. So just a nice feature that we wanted to point out of how easily it is to scale with this GM3 package.
Yeah, that's excellent.
To further demonstrate the scalability and how easy it is to take your present FM3 based system and upgrade it to our new GM3 system, we wanted to go through and demonstrate a simulation study of the 2-level grid-tied converter that you see on the screen. So for this grid-tied converter, we considered a 480 volt line-to-line grid voltage with 100 microhenry inductors. So with that, a decently high switching frequency of 50 kilohertz would be our baseline for the study. And then a bus voltage of 800 volts. And for this case, a heatsink temperature of 50 degrees C. So first, again, to understand kind of this upgrade path, we wanted to assume we have a baseline system based on our FM3 half-bridge module. So based on the implementing this FM3 half-bridge module into this grid-tied converter, we see that we really push the bounds of this module and limit it to 75 kilowatts at 50 kilohertz before we reach the rated junction temperature of 150 degrees C. So if we wanted to upgrade this system with our GM3 module, and if we simply put the GM3 into this same system at 75 kilowatts and 50 kilohertz, we see that the junction temperature would actually be lowered to only 114 degrees C. So again, this is using the next RDS(on) variant, so the 8 milliohm GM3. So we do increase the die area, decrease that on resistance, so we're getting lower losses for that 75 kilowatt, 50 kilohertz system. So reducing the junction temperature could provide benefits because it could help you use a smaller heatsink if desired, or you can increase the heatsink temperature if that's needed. So both of those are kind of cost-cutting measures. Or we could get, with a lower delta T, we could get more lifetime out of the devices because our power cycling capability would be increased with a lower junction temperature. So that was junction temperature. Now, if we wanted to increase power for our system, we see that with the 8 milliohm GM3, we can actually achieve 100 kilowatts at 50 kilohertz before we reach that 150 degrees C junction temperature limit of the devices. And likewise, if it was our design goal to increase the switching frequency because we want to reduce the size of the magnetics or other BOM components, then we see that at 75 kilowatts, we can actually increase the switching frequency to 85 kilohertz. So when we talk about upgrade path, we don't necessarily just mean with power, but really with switching frequency and junction temperature in terms of decreasing the junction temperature. So looking at the kind of the bounds, what can be done by just simply moving from the FM3 to GM3 in this system, Again, we can increase power, increase switching frequency, or decrease junction temperature, or a combination of all three, all depending on what your overall design goals would be.
That's really helpful because those three areas not only are so important, but typically, if you need to get more performance in one of those, you're going to suffer in the other two. So getting advantages in all three is pretty exciting for system designers.
It is. And that's one thing that with this new package, we're getting better utilization of the silicon carbide devices and really getting that capability to provide that scalability across multiple system variables.
And all of this, as you noted, is for your 8 milliohm system, but that isn't even the highest performance product in your GM3 family, is it?
That's correct. So like we went over, we have an 8 milliohm and a 6 milliohm GM3 half bridge module. So the previous slide, we kind of went through the case study of going from our 11 milliohm FM3 to our 8 milliohm GM3. But with this next case study, I kind of just wanted to touch on the capabilities that you could achieve with the 6 milliohm GM3. So if we went through the exact same exercise that we just went through on the previous slide, I won't go through it all again, but just looking at those bounds, we can see that, again, the power can be increased, the switching frequency can be increased, or the junction temperature can be decreased, even over our new 8 milliohm baseline system of 100 kilowatts at 50 kilohertz. So you can easily see the increases that you could achieve over the 11 milliohm FM3 with the 6 milliohm GM3, but you still even get performance increases over the 8 milliohm GM3. And these, of course, are both with the standard alumina substrate. And next, I'll kind of discuss the aluminum nitride substrate and how you can really push the performance of these modules up with that. So now considering the 6 milliohm alumina version as our baseline system, really to kind of push the bounds of that grid-tied converter, we see that at 125 kilowatts and 50 kilohertz, we're maxing out the junction temperature at 150 degrees C. So if we go through the same exercise again as the previous two slides, then by replacing the alumina 6 milliohm version with the aluminum nitride 6 milliohm version, we can really push the performance up significantly. So all the way up to even 170 kilowatts at 50 kilohertz. And so this is where really the GM3 starts to bridge that gap to those higher power module solutions as we approach these higher kilowatt ranges. And similarly to the previous two slides, at 125 kilowatts, we can almost double the switching frequency from 50 to 95 kilohertz. So again, this creates some system level benefits in terms of magnetics or other passive components that could be reduced in terms of size, which correlates to a reduction in cost, or even, again, reducing the junction temperature from 150 C to 109 C at 125 kilowatts and 50 kilohertz. So reducing the junction temperature by roughly 40 degrees C will help with the lifetime of your system, or again, provide those benefits from the heatsink perspective, and just give you more overhead and really start to utilize the silicon carbide device performance.
Yeah, you've kind of touched on all this, but the overall system cost reduction by reducing the cooling or reducing the size and cost of the magnetics, or even lowering the temperature so the lifetimes increase, there's a lot of downstream benefits that each of these individual improvements also mean to the overall system.
That's exactly right. And that's where this Wolfspeed Wolfpack family as a whole, that's really the main design theme and the goal of this package family that can be scaled and implemented fairly easily, and really consider the system level performances that can be achieved by using the GM3 versus the FM3 module. It's not always just about power, and we haven't really touched on efficiency, but all these case studies, it's all very high efficiency grid tied converter. But again, we wanted to demonstrate that scaling and the flexibility of these packages not only means power, but also you can think in terms of other really critical and important system level variables that, depending on what your design goals would be very important to you as a designer.
Yes, exactly. So tell us a little bit more about this aluminum nitride package.
So if you look at the typical thermal resistance from junction to heatsink contribution for these base plateless modules, you can kind of see that the thermal interface material or the thermal paste and the DBC substrate make up the overwhelming majority of the RTH contribution, so 90% together. So with our standard alumina version thermal interface material, the customer has some control over the thermal interface material, but really the alumina version might be a little more cost sensitive. So if we wanted to push the performance of these modules up, what we have more control of from a module manufacturer standpoint is the substrate. So if you go to aluminum nitride in conjunction with a high performing thermal interface material, that 90% contribution manifests itself in roughly a reduction in the thermal resistance by over 50%. And so this is really due to aluminum nitride offering a 7 times higher thermal conductivity over alumina. So even at a thicker substrate thickness, the thermal resistance is dramatically reduced. So similar to the themes that we previously discussed with our simulation study, this allows a lower junction temperature for a given loss and enhances the power cycling lifetime for a given loss. Or conversely, enables a higher heatsink temperature or a smaller heatsink, which is a cost consideration. And then finally, again, just higher utilization of our devices. So at some point, the devices are always package limited. And so if we can improve the performance of the package, we'll get better utilization of our devices.
Yeah, that's some pretty impressive improvements in the performance just by changing the package. And I really shouldn't say just through changing the package, because that is some pretty amazing engineering that's going on inside there. So Jonathan, for the viewers now who are getting excited by what you're doing here at Wolfspeed with your silicon carbide products and these new GM3 offerings, what's one of the easiest ways for them to move forward?
Yeah, so Wolfspeed, what we try to do as a company is provide you with all of the tools that you need to not only evaluate our products, but really adopt silicon carbide as quickly and efficiently as possible. So what we offer is quite a few evaluation tools, which I'll be happy to go through now. So one of the first tools in terms of hardware that we provide is a dynamic evaluation board. So like many of our products, power module platforms, we have a dynamic evaluation board that you can purchase or test drive. But the main idea of this board is that we can get a very well characterized setup into your hands as quickly as possible. So then you can start doing dynamic evaluation on your own. So dynamic evaluation would be clamped inductive load tests or double pulse tests. So really what you're looking at is the switching loss performance over multiple variables: bus voltage, current, junction temperature, gate resistance, and also the timing of the devices, the VDTs and DIDTs, overshoots and things of that nature to help just get you more familiar with the performance of the package and kind of the limits. And what we try to do is provide a nice system for you to conduct these tests on your own without having to spend much engineering time from the end user perspective, because you're taking our engineering time and our knowledge and expertise as silicon carbide power module manufacturer and really taking advantage of that and being able to move forward quickly in terms of dynamic evaluation.
So is the GM3 module on the back side of this eval kit? I don't see that white package that we have seen earlier in this presentation.
Yeah, so it's on the underside of this board. So this is a PCB board that contains the bulk capacitance needed to conduct the clamped inductive load test. It contains a high frequency shunt current viewing resistor to provide a high fidelity current measurement. And then we have multiple Kelvin voltage connection points. So you can look at drain to source voltages, gate voltages, things of that nature. All of the critical important signals that go into looking at the dynamic performance. But the GM3 module itself plugs directly into this board from the bottom. So this board actually utilizes sockets. So we wanted to use socketed connections so we don't compromise the connection of the board itself. So the press fit style pins are only designed to be inserted and removed a few times before that connection becomes compromised. So with the sockets, you only need one dynamic evaluation board and you can evaluate multiple GM3 variants or multiple modules of the same on resistance variant at a time.
Oh, very nice. What are the other components that a user would need to get started using this evaluation kit?
Yeah, so not only is a well-characterized power board required, but another big aspect that affects the dynamic performance of the module is the gate drivers. And so what we've done is partnered with 3 companies to develop reference gate driver designs, each with its own unique set of functionality and protections and performance. But really, the dynamic evaluation board is designed for these partner gate drivers to plug into so that you can evaluate the driver module combination. Because that's a critical feature to understand, not only in terms of the performance of the module, but how the gate driver is affecting that performance and the protections of that gate driver and things of that nature. So evaluating both in conjunction on this board is critical. And another tool that Wolfspeed provides is a 2-channel differential transceiver board. So this is a highly recommended tool that we have available on our website. So what this does is it takes single-ended signals, which most people have access to generating a single-ended signal of some sort, and it converts it to differential, which each of our partner gate driver boards has the same differential signal inputs. So you might be asking why differential signals. With the faster switching rates of our silicon carbide devices, using pure only single-ended signals, you could get some noise getting in based on from the radiated switching noise of the devices, because we do have high DVDTs and DIDTs. So the differential signals really increases the noise immunity, and using these tools properly and as we recommend really reduces the impact of that radiated switching noise. So you're not fighting the system that you're trying to evaluate. So we try to provide the tools for you so that you can focus on the evaluation of the module without worrying about everything else around the module.
Yeah, that's a lot of current that you're switching really fast. So that would certainly be creating some pretty significant spikes, which is going to make taking test data challenging. Now, what are some of those other resources that you have available to support the designers?
So we recently released application notes for the FM3 style package over this past year. So what we've done for this release of the GM3 style package is we've gone back and updated those application notes to include the new information for the GM3 platform. So this creates more of a comprehensive Wolfspeed Wolfpack platform guide. So you can go to our website and download these primarily for guidance on application of thermal interface material or mounting instructions and PCB requirements for both the FM3 and GM3. So these 2 application notes are again available on our website and include the new information for the GM3. Another tool that we highly recommend for initial evaluation of the GM3 platform is our Plex thermal models. So we provide these models as a download on our website. So if you have Plex standalone or block set, we recommend you to go and download these models. And what you can do is plug these into your system that you've designed in Plex, very similar to what I went through with our simulation study. And understand what the performance of the module, the GM3, would be within your system. So this really helps you find the best fit, we have 4 variants of the GM3, so which one would be best for your system and for your design goals. But if you don't have Plex, no need to worry. We actually have a web-based online simulator that we call SpeedFit 2.0 Design Simulator. And what this is again, it's web-based and it comes preloaded with all of our module thermal models and many common converter topologies, like the 2-level grid-tied converter or active front end, many DC-DC converter topologies and neutral point clamped and other things like that. So really, it takes only a few minutes to get a simulation, which is run in the background and provides you with kind of the performance of the module and the devices within the system that you've defined. So this is a very simple and quick first tool that you can use. And again, recommend to go to our website and check this out.
So Jonathan, that just about wraps things up for us today. Can you put a bow on this presentation for us?
Yeah, and everything that I've discussed throughout this presentation is really available online as an online resource at wolfspeed.com. So again, we really try to provide all of the information and tools needed to quickly adopt our silicon carbide power products. So everything from the SpeedFit design simulator, reference designs, the dynamic evaluation kit, the application notes, and even a knowledge center that contains white papers and other presentations and webinars that we've given are all available online. So once again, just highly recommend that you visit our website and under tools and support and check out all of our available resources.
All right. Thank you, Jonathan, for that excellent and detailed presentation today. I really think that our viewers are going to find that helpful as they get started designing with these new GM3 modules.
Yes, thank you for having me, and I've enjoyed our time and our chat, and I hope that our audience has found this information useful and they've been able to learn about our new GM3 module platform.
As we wrap up this edition of Tech Chat, we want to thank Jonathan Hayes of Wolfspeed for introducing us to their new GM3 line of advanced silicon carbide power modules, and also Mouser Electronics for their sponsorship of today's program. And be sure to join us next time on Tech Chat, where we chat with industry leaders, like Jonathan, about the latest advancements in electronics technology.